Hey, welcome back. In this video we are going to talk about alkene reaction and we are going to dive to the most common reactions of alkenes. So without any further ado, let's dive into them. Let's move now to the oxidation of alkenes. First one is epoxidation that occurs in syn stereochemistry. Take a look at this cyclohexene. If we treat this with meta-Chloroperoxybenzoic acid, this is a specific compound, meta-Chloroperoxybenzoic acid, in dichloromethane solvent, we are going to yield an epoxy product that occurs in syn, that means on the same side. This is an epoxy group. Okay? If you want to place name, is 1,2-epoxy cyclohexane. Another way to do epoxidation is by forming a halohydrin, as you can see here as we learned above, and treating the halohydrin with a base. So this base here is going to attack this hydrogen, and this bond is going to move here, and this chlorine is going to move away to respect the octet rule. So we are going to have here the formation of epoxide. Okay, again name 1,2-epoxy cyclohexane. If we acid-catalyze the epoxide group, we are going to have the formation of a diol that happens in anti. That means that this diol is going to be trans. So from epoxidation, from an epoxide group, if we treat with an acid-catalyzed, we are going to have the formation of a Trans-diol. Okay? In terms of mechanism, this oxygen is going to take this hydrogen here, and we are going to have the formation of this product. And the water molecule is going to attack on this side, and this ring is going to open here to stabilize the oxygen, and we are going to have the formation and here we are going to have this in order to keep it in trans. So here are hydrogens, okay? So now another molecule of water is going to catch this hydrogen, and this is going to be stabilized here. So the final product is going to be a Trans-diol. Okay? A Trans-diol. Trans-1,2-cyclohexanediol. In case you wonder for the name. Okay, so now we learn a way to yield a diol in trans. But there is another way to yield a diol in cis by treating an alkene with osmium tetraoxide. And first we are going to have the formation of this cyclic osmate. As an intermediate, and after that, by treating with sodium bisulfite, you're going to have the formation of a Cis-diol. Okay, Cis-1,2-cyclohexanediol. If you want to yield a Trans-diol, up to now we learned that we can form epoxidation, and we can treat that with acid-catalyzed. In order to form a Cis-diol, we can use osmium tetrahydride and a sodium bisulfite in 2 steps, okay? But the problem with osmium tetraoxide is the fact that it's very expensive and also is very toxic, not pyridine. Pyridine is a common solvent in organic chemistry, in case you want to know the structure. Something like this. Instead of that, we use a co-oxidant called N-methylmorpholine or NMO. So we use osmium tetraoxide in catalytical amount. So first we are going to have again the cyclic osmate. And after that, with this co-oxidant, we are going to yield a Cis-diol. This is called also NMO in a shorter way, plus the remaining of the co-oxidant. And the cycle continue and continue to yield this Cis-diol in an economical way. Let's move now to the cleavage to the carbonyl group. We can break the double bond in two common ways. First is by ozone, this one here, and followed by treatment with zinc as a reducing agent. The second way is by using an even stronger oxidant that is potassium permanganate. Okay? The first one is going to break the double bond in case you do not have hydrogens, like in this carbon here, because it's going to get another carbon-carbon and double bond here 4. It is going to form a ketone, always, if you do not have hydrogens. In case you have hydrogens here, 2 hydrogens, is going to form an aldehyde in case of ozone. So, if you have hydrogens, is going to form aldehyde in case of ozones, 1 or 2. If you do not have hydrogens at all, is going to form ketone in case of ozone. Let's move now with the same compound in case of potassium permanganate in acidic medium. In this case, this double bond here is going to break, and in the case that you do not have hydrogens, is going to form a ketone. But in case you have 2 hydrogens, it's going to oxidize completely to form carbon dioxide. Okay? What about in case you have 1 hydrogen? What is going to happen? Take a look at this example here. In case here, you have to break this double bond here. Also break the cycle. So let's write it as it is. So in this side here, you do not have hydrogens. So it's going to form a ketone. But on this side here, you have a hydrogen. In case of potassium permanganate, it's going to form carboxylic acid if it's only 1 hydrogen. If there are 2 hydrogens, you're going to form carbon dioxide, like in this case above. So the oxidation goes further, does not stop to aldehydes. In case of ozone, you are going to break again the double bond, but in case there is no hydrogen, again it's going to be a ketone, but in case you have presence of 1 hydrogen, you're going to form an aldehyde. Okay, keep in mind the difference. So potassium permanganate is gonna form ketone in case no hydrogens. In case of 1 hydrogen, is gonna form carboxylic acid, like this one here. In case of 2 hydrogens, is gonna form carbon dioxide. In ozone, in case you do not have hydrogens, it's gonna form a ketone, the same as with potassium permanganate. But in case you have 1 hydrogen or 2 hydrogens, you're gonna form aldehydes. Okay. Another way to break the double bond is by forming first a diol by treating with osmium tetraoxide and NMO. Here you are going to have the formation of a diol that is in cis, not like epoxidation and acid-catalyzed to form a trans-diol. Here you have in cis. Okay, and if you treat this diol with periodic acid is this one. Okay, in water and THF as a solvent, you're going to have the formation of this intermediate And after that, you are going to have a break in this bond here and the formation of aldehydes. In case you have no hydrogens present, you are going to form a ketone. In case you have hydrogens, you're going to form a aldehyde. Keep in mind this. With periodic acid. Let's move now to addition of carbenes to alkenes. Cylopropane synthesis. Carbene is a 2-valent carbon, very reactive due to the empty orbital. Carbon here is 2-valent, okay? This is a very active species and we cannot isolate it, so we can generate it as an intermediate during the reaction. Let's take a look at this cyclohexene. Treatment of this with trichloromethane in a basic condition is going to yield a cyclopropane chlorinated. So it's going to give this. Is stereospecific. In case you start with cis, you end with cis as a product. But this way of yielding cyclopropane, it works, but you have that chlorinated. In order to do that pure without chlorine, you need to use the Simmon-Smith reaction. Simmon-Smith is the best method for preparing non-halogenated chloropropanes. The process is called Simmon-Smith reaction. It utilized a carbenoid metal complex reagent, iodomethyl zinc iodide. This is a carbenoid. First, we have the reaction of diiodomethane with zinc copper mixture, and we have the formation of this carbenoid. This carbenoid, after that, is going to react with alkenes, and we are going to have the formation of cyclopropane without chlorination. Okay. And the zinc iodide as a byproduct. So keep in mind this Simmon-Smith to yield cyclopropanes. Hope this video was helpful to you, and thank you so much for watching, and see you in the next video. Peace.